I'm Ruotong from the University of Utah. It's a great pleasure to present our paper. Ground truth for binary disassembly is not easy. This is a joint work with Chengbin, Tiantai, Zhang, and Professor Bing Mao from Nanjing University, and Professor Jun Xu from the University of Utah. So binary disassembly is a process of translating a binary executable to assembly file. During this process, the disassembler will handle several tasks, include instruction recovery, function start detection, control flow graph reconstruction. Binary disassembly is also the core component of many applications, such as code similarity detection, vulnerability discovery, and binary code patching. So generating ground truth for binary disassembly is very important. For instance, many machine learning models like byte weight relies on the ground truth for training purpose. On the other hand, if we don't have the ground truth for binary disassembly, we won't be able to verify the disassembly result, and the user won't be able to pick the best performance disassemblers. Although everyone is aware of the importance of ground truth for binary disassembly, they have less agreement on the way of generating ground truth. So here we summarize all the mainstream approaches of generating ground truth for binary disassembly. So first is the manual analyze. So this approach relies on manually crafted ground truth. So the second approach is using the existing disassemblers. For instance, some people would just borrow the result from IDA Pro as the ground truth because it has the stable performance. On the other hand, intermediate compiler output could also be used for generating ground truth. For example, listing file generated by the assembler contains the information of instruction, and this information could be used for generating ground truth. Similarly, compilation metadata such as symbol and debug information could be used in a similar way. And the last approach is tracing compiling process. We will discuss more detail about this approach in the later slides. So far, we have discussed all the mainstream approaches of generating ground truth. To understand the quality of the ground truth generated by different approaches, we will evaluate them from 4 aspects. So the first is the precision, and the second is recall, third is generality, and the last one is the extendability. So the precision basically reflects the correctness, and recall reflects the coverage. Generality requires the ground truth approach support various disassembly tasks, such as jump table recovery, control flow recovery. And extendability requires the approach can be applied to multiple architectures. So previously, we have known, so let's going back. So according to this table, we can see none of this approach is actually perfect. So for instance, running manual analysis is not doing well on the recall. Reusing existing disassembler needs improvement on precision and recall. Relying on intermediate compiler result or compilation metadata needs improvement in the generality, and tracing compilation process needs improvement on the extendability. So as we have seen, none of this approach is perfect. So here comes the next question. How is the imperfect ground truth will influence the disassembly, binary disassembly? So let's begin to answer this question with the result from a case study. So this table presented the performance of byte weight trained with ground truth produced by 2 different approaches. So the symbol refers to the ground truth generated based on symbol information, and oracle refers to the ground truth used by our SOK paper, all you ever want to know about x86 and x64 binary disassembly, but were afraid to ask. So the oracle is designed based on intercepting the compiling process. So as we can see from this table, there is observable differences between the precision under the OF setting when byte weight is trained with 2 different approaches. So that leads us to the finding the fidelity of ground truth affects disassembly to design. So we did another experiment by evaluating disassembler with different ground truths. So this table presents the performance of Dennis on identifying complex constructs with ground truths produced by different approaches. So according to this table, Dennis achieves the perfect performance on manually crafted ground truths. It achieves 100% precision and recall, but this number significantly drops when we evaluate it based on Oracle. So this leads us to another conclusion. The use of incomplete or imprecise ground truths will lead to misleading conclusions. So previously, we have presented enough evidence showing that imperfect ground truths will not only lead to contradictions, but also affect the disassembly to design. So it's very important to improve the ground truths into a better position. So in this paper, we decided to follow the direction of tracing compilation process because it has the best potential. We can see from this table, Oracle has the very good performance on precision and recall. So we decided to improve Oracle from the other two aspects. So we will first handle the missing cases in Oracle to improve the recall, and also we will extend Oracle to support more architectures. So before we discuss the improvement we made, I would like to begin the discussion on how tracing compiling process works. So here, according to this table, we can see the Oracle will instrument the GCC front end, the gas assembler, and the Go linker to insert metadata to the output at different compilation stages. So the metadata is stored into the object file, and the ground truths will finally be recovered based on the metadata. So the internal mechanism for Oracle's design is same for both GCC and Ceylon. So now let's move on to the first major improvement we made. So I'd like to begin the discussion here by answering the question why there are corner cases exist in Oracle. So in the first case, the instructions are failed to be recognized by Oracle during the assembly process because the instructions are intentionally encoded as data by the developers. So the developers are doing so because some version of the assembler may not always support such instructions. So encoded the instruction by row byte can successfully bypass the assembly process. So the second example is a handwritten assembly code from OpenSSL. So such handwritten assembly function may not always be properly labeled. So in both of these cases, compiler is not involved in the process of generating this assembly code. So as a result, Oracle is not able to handle both of them because intercepting the compiling process doesn't help in both cases. So the second major improvement we made is to extend Oracle design to more architectures. So the original version of Oracle only support x86 and x64 binaries, and we extend it to support more architectures, including ARM32, ARC64, MIPS32, and MIPS64. So during this process, when we are trying to handle, to support more architectures, there are also challenges we need to solve. For instance, while generating the ground truth for ARM32 binaries, we need to keep track of the execution mode. So to do so, we save extra information to the metadata for each basic block. So to demonstrate the benefits of our improvement to the Oracle design, we evaluate the accuracy of 6 popular disassembly tools on recovering jump table from glibc. So this figure presented the evaluation result. So as we can see here, in case of the IDA Pro, its performance varies between the improved version and the original version. And the number is pretty large, over 60%. So the key observation here is that our improvement to the oracle helps the understand of true accuracy of this assembly tool. So given the better ground truths, we again evaluate the performance of modern disassemblers. So this figure presented the precision of mainstream disassemblers on binary with different architectures. So according to these tables, we can see the performance of modern disassemblers vary across the architectures. For instance, we can see Object DOM could easily achieve over 90% accuracy on most of the architectures, but its performance significantly drops on ARM32 binaries. In fact, ARM32 usually poses a bigger challenge than ARC64 because of the execution mode. So the second observation comes from the commercial disassemblers. If we looking at the figure C, we can see both B and C. We can see disassemblers like IDA Pro and Binary Ninja doesn't doing well on the MIPS binaries. So at the very end, I would like to share with you our code is available on the GitHub repo, and our paper passed all the USENIX artifact evaluations. You are welcome to investigate our paper and code for more details. This is about my presentation, and thank you so much for your listening. The first author of this paper, Chengbin, and I would like to answer any of your questions.